The Physics of Interstellar Travel. Chapter 4, Orbital Mechanics. It might seem odd that a book on interstellar travel would include a chapter on orbits around stars and planets, given that the whole point of interstellar travel is not to be confined to orbit around a star or a planet. That's true, but if an interstellar spacecraft wants to go into orbit at its target system, we need to know how it can lose its energy and angular momentum. Furthermore, there are a couple of interesting phenomena that can be used to increase or decrease the energy of a spacecraft. These are the gravity assist and the Oberth effect. Let's first look at the gravity assist. The purpose of the gravity assist is to accelerate a spacecraft relative to a star by passing close to a planet that is orbiting the star. Remember, accelerate means change the speed and/or velocity of the spacecraft. The gravity assist was most famously used by the Voyager 2 spacecraft on its grand tour to the 4 outer planets in the 1970s and 80s. The spacecraft used the gravity of each planet to deflect its trajectory such that it would intercept the next planet on its journey outwards. The sharp turns you see in this plot at each of the planets were achieved without using any significant boosts from the engines. But not only changing direction, the gravity assist at Jupiter, Saturn, and Uranus also increased the speed of the spacecraft relative to the Sun. We see from this figure that the gravity assist at Jupiter accelerated the spacecraft enough that it would be able to escape from the solar system. To see how the gravity assist works, consider a spacecraft, shown here as the lower point in blue, in the rest frame of a planet, shown here as the upper point in orange. Both the spacecraft and planet are orbiting around a star, but to demonstrate the gravity assist, we can ignore the star's gravity. The spacecraft is moving relative to the planet, but it's moving too fast to be bound to it by gravity, meaning that it is moving on a hyperbolic orbit about the planet. As the spacecraft approaches the planet, the gravity accelerates it and deflects its path. After passing the closest approach point, the periapsis, which is at time 0 here, gravity acts to decelerate the spacecraft as it moves away. The spacecraft's trajectory is symmetric in time and symmetric in space about the orbit's axis, that's the x-axis. So if we compare any point in time before and after the periapsis, the spacecraft is moving at the same speed, but in a different direction. So how was it possible for Voyager's gravity assist to increase the speed of the spacecraft? This is all a question of reference frames. While the trajectory is symmetric in the reference frame of the planet, it is not symmetric in the reference frame of the star. This is because the planet is moving relative to the star. If we now look at the spacecraft's trajectory in the reference frame of the star, as shown in the video on the right, we see quite a different motion. The spacecraft is now moving faster relative to the star after the encounter than it was before the encounter. This occurs because this planet has changed the direction in which the spacecraft is moving, so the vectorial velocities now add up differently. In this particular configuration, the spacecraft passes behind the target planet, and this causes the spacecraft to accelerate in the reference frame of the star. But we can also arrange for the spacecraft to pass in front of the planet. The motion of the spacecraft relative to the planet, as shown on the left, is the same as before. But because the periapsis now occurs at a different point relative to the direction of travel of the planet, the spacecraft is now decelerated, as we can see in the video on the right. Take a moment to compare these two videos, the spacecraft passing behind the planet in the top panel and the spacecraft passing in front of the planet in the bottom panel. In reality, the motion is a bit more complicated because the planet and spacecraft are actually orbiting the star, but the principle remains the same. In fact, gravity is not central to this phenomenon. We get the same effect when bouncing balls off moving object, as I explained in the chapter. The key aspects are changing direction and changing reference frame. Let's now turn to the other phenomenon, the Oberth effect. For a spacecraft moving at some velocity in a reference frame, its kinetic energy per unit mass in this reference frame equals half the magnitude of its velocity squared. Let's suppose this spacecraft is in free space where gravity is negligible. The spacecraft fires its engines to change its velocity by some amount delta v. Velocity is a vector quantity, so the final velocity is the vector sum of these two velocities. The final kinetic energy per unit mass is now half the magnitude of v plus delta v squared. Thus the change in kinetic energy to this delta v, due to this delta v, is given by half v squared plus the scalar product of v plus delta v. That's just kf minus ki. So this equation on the right tells us two things. The first is rather obvious. To maximize the increase in the kinetic energy of a rocket using a given delta v, we should apply that delta v in the same direction as the rocket is traveling. The second thing we learn is perhaps less obvious. To maximize the increase in the kinetic energy, we should make the magnitude of v as large as possible. That is, we should apply the delta v when the rocket is moving fastest. This becomes relevant when we now consider our spacecraft in an elliptical orbit about a star. We want to use our rocket engines to escape from the star and achieve the largest velocity possible when far away from the star, technically when we get to infinity. Where in the orbit should we apply the rocket engine boost? From what we just considered, we should apply the boost at periapsis because that's when the spacecraft is moving fastest. Using conservation of energy, we can derive an expression for the velocity of the star at infinity, velocity of the spacecraft, at infinity, in terms of the initial velocity vi and the boost delta v. How effective is this? Suppose a rocket starts off in a parabolic orbit about the Sun that takes the rocket within 10 solar radii of the Sun. A parabolic orbit, remember, is one on the edge of being bound and unbound, the transition between an elliptical and a hyperbolic orbit. Without any boost, the rocket would therefore reach infinity with a velocity of 0. Suppose our engines can provide a boost of 5 kilometers per second. If we apply the boost when the rocket is at infinity, then the final velocity of the rocket is of course just 5 kilometers per second. But when the rocket was at periapsis at 10 solar radii, it was moving at 195.4 kilometers per second. So if we could apply our 5 kilometers per second boost there, then the final velocity at infinity, given by this equation, will instead be 44.5 kilometers per second. We have gained nearly 40 kilometers per second in speed for free just by applying the boost at the optimal point, namely the periapsis. This is the Oberth effect, and it is ultimately a consequence of the quadratic dependence of kinetic energy on velocity. While this optimization is useful in some context, a velocity of 44.5 kilometers per second is not nearly enough for interstellar travel. Even if the rocket could approach much closer to the Sun, which is difficult in practice due to the heat, and so get an even larger initial velocity, and if we could use a much bigger rocket to get a larger delta v, this application of the Oberth effect will not help us in practice for getting to the stars quickly. The velocities are simply too small. But we will see in Chapter 10 how diving close to the Sun could achieve much larger velocities when using a solar sail. So I've summarized two interesting aspects of Keplerian orbits: gravity assists and the Oberth effect. These are explained in more detail in the book chapter, where I also summarize the essentials of Keplerian orbits, both open and closed. I also discuss the most basic orbital maneuver to move between two closed orbits, the so-called Hohmann transfer orbit.